folks. Special Quiz 2 is practically speaking ready to go, but I want to polish up the way by which I ask the questions regarding a particular and important consideration on Special Quiz 2. So I've not published it yet. What I intend to do is to, as I did for Special Quiz 1, make available by handout Special Quiz 2 for you folks here on Friday. So you can just pick up the copy. But it'll also be on Sakai if you wish to download it. But it may well be on 8.5 by 14. And I don't know if you're capable of downloading 8.5 by 14. In any case, it doesn't matter because I'll make it available to you for pickup. The issue that I intend to expose you to regarding Special Quiz 2 is the fun and games that chemists have in dealing with data. Where does the data come from? It comes from experiment and measurement. You think it's likely that research group A and research group B will get the same values for the experiments and measurements if, for example, the measurements are being made on a system where concentrations have to be observed, and the concentrations which have to be observed are very, very, very small. You think very, very small concentrations are easy to observe correctly? So, in designing Special Quiz 2, I had intended originally to consider treating a solution of silver nitrate, because that's one of the very few soluble silver salts, with a source of phosphate ion, hydroxide ion, and ammonia. Which would give you in the resulting system silver ammonia complex ion, silver oxide precipitate, silver phosphate precipitate. And then have fun analyzing the composition of this system at equilibrium. And I found out with the data available, I was getting results which didn't make any sense. So I looked more closely at this. In particular, I focused on silver phosphate and silver oxide. Because if you take the KSP information that's available for our use, that's on the information sheet, which I fished out of reference books, and consider treating silver oxide with a source of phosphate ion to convert it to silver phosphate. With the available data, you'll get a very small K value, something on the order of 10 to the minus 7th, if I did the arithmetic correctly. Well, that supports the conclusion that treating silver oxide with a source of phosphate ion really isn't going to convert the silver oxide to phosphate ion. But this doesn't make sense. It doesn't make sense because I looked up the measured solubility values for these two materials to find that silver phosphate, based on the data I saw, is a lot less soluble, which means more stable in water than silver oxide. So what does that mean if I treat silver oxide with a source of phosphate ion? If the silver phosphate is less soluble, is it more stable or less stable than the silver oxide in water? More stable. So if you treat the silver oxide with the source of phosphate ion, there ought to be a substantial degree of conversion. But with the data that we have on the information sheet, nothing. Well, I'm going to ask you to go through this on Special Quiz 2. I will direct you toward the data that you're supposed to use for all considerations that I ask you to make. The ultimate upshot of which is, with this analysis, we will be so bold and audacious as to go to the information sheet and replace the existing value for the solubility product for silver oxide, as well as the existing value for the solubility product of silver phosphate. Because I believe the measured solubilities are going to be fairly reliable pieces of information. But the KSPs, which I have observed, don't come from these measured solubilities. Pardon me, the KSPs, which you see on the information sheet, don't follow from these solubilities. So I'm going to ask you to calculate what I will believe to be the correct solubility products. And then we'll pay attention to the treatment of silver oxide with phosphate, a source of phosphate ion, and convert it to silver phosphate, and then see what we get. We've already made the decision that there should be a substantial degree of conversion based on the solubility information. One more comment. Silver phosphate. Notice that I'm doing something I rarely do. That's providing you some specific information on how to wrestle successfully with a special quiz. But we're just getting you familiar with thermodynamic data. We're going to talk about such today. And how to use it. And where does it come from? So I want to give you a reasonably good foundation on this. Remember a moment ago I commented that silver phosphate based on solubility data. That's got by direct measurement. Silver phosphate's not very soluble at all. So the question is, do you think that if I want to get KSP for silver phosphate, that this is the correct reaction to use? Yes or no? Why not?
It can't account for the...
What very important property of phosphate ion in this system is neglected by this reaction equation?
Strong base.
Strong base, not a strong base. Look at the acid-base table. But has it got a Kb value that's appreciable? So I ask again, in the saturated solution of silver phosphate, what important property of phosphate ion is neglected by this reaction equation? Well, that's on Special Quiz 2. Think about it. And so we proceed. Have I caused sufficient mystery for you? I should hope not. Because, for example, when we went about the business of calculating the solubility of calcium carbonate in water, you can't just look at the KSP equilibrium. What else did we have to look at? Enough said. Now, Table 1. End of chapter 20. Open it up, your notes to that. Thermodynamic properties of substances. There's two types of substances considered in this table. Pure substances, elements and compounds, and special species. What are the special species to which I refer?
hydrated.
You see them in the table? Hydrated ions, ions in water solution. Did you recognize in Chemistry 2045 that if we're going to get thermodynamic property information for ions in water solution, we have to invent a thermodynamic reference point? Did you learn that? I can't use the third law of thermodynamics to get at this. Third law of thermodynamics gives me an absolute reference point for entropy. It says at absolute zero, the entropy of a perfect crystal is 0. Can I take a solution, absolute 0, and have the solution remain in existence? Yes or no? Hell no. What's going to happen? As I cool the solution, sooner or later, what's going to happen? Water's my solvent. As I cool the solution, what's going to happen? What's going to happen? You think the solvent might freeze? You ever eat a popsicle? You like popsicles? I like popsicles. Is popsicle a solution or a suspension? It's a suspension, isn't it? It's solid phase. Because when you freeze, the solution, the solvent, separates from the solute. How about that? Did you learn that in 2045? More on that in a while. In sum, what I want you to do now is to get familiar with this thermodynamic property data table, because I believe it's a fair statement that there's more chemistry stored in the thermodynamic properties data table than any other single compilation or table in existence. All the equilibrium constants we've been talking about can all be calculated from the information in this table. KSP values, K values, KB values, KF values, all come from information the likes of which you see in this table. Now, the table we have at the end of chapter 20 in our notes is rather comprehensive, but it's not totally comprehensive. I don't want to put about the 50 or 60 pages of thermodynamic properties information that's available in the National Bureau of Standards circular, whatever the number is. About 60 pages of all chemical substances and species like the ions in solution for which these thermodynamic properties have been measured. Now, as it relates to what I was mentioning about special quiz number 2, you think it's fair to believe that every datum that's in this table, every number you see is correct? You don't believe it. At the minimum, if you want to be successful in science class or be successful as a scientist, you must always be a skeptic. Don't believe anything. That doesn't mean you disbelieve it, but it doesn't mean you believe it unless you've got reason, evidence to believe it. Then you can believe it. But without the evidence, don't believe it. Always be skeptical. Always be critical of any information that you're asked to consider in science class. Don't think anything I say for granted as a statement of truth. Don't do that. You question everything I say. And that way you'll learn best. In any case, we'll ask a specific question regarding this thermodynamic property data table. Look at carbon. There are 2 allotropes of carbon, although now there's arguments for 3. Buckyball carbon is also considered to be an allotrope of carbon, or even carbon charcoal. But the principal allotropes of carbon, graphite and diamond, with which I'm sure you're familiar. How many of you right now are making scrawls on paper with carbon graphite? Okay. Anybody making scrawls on paper with carbon diamond? You could record your notes with carbon diamond. Your notes would be a collection of scratches. Scratches in the paper. Because when you shove the carbon graphite across the paper, obviously you see a smear of graphite. But if you shove the carbon diamond across the paper, you're not going to leave any carbon atoms. You're not going to fracture any of the carbon diamond by this activity, but you sure will tear the hell out of the paper. Because carbon diamond is a lot harder and more durable than carbon graphite. But now, take again a look at this information in the table. Look specifically, delta H sub F super 0 for carbon graphite versus carbon diamond. You see the value 0 and plus something or other? For which of these samples of carbon is the plus delta H sub F super 0 value? Diamond, isn't it? That means converting carbon graphite to carbon diamond is, from a change in enthalpy standpoint, favorable, yes or no? No. Not favorable. How about that? Because the carbon-carbon covalent bonds in graphite are stronger than the carbon-carbon covalent bonds in diamond. Stronger. So how the hell is it you're tearing up this carbon graphite pencil when you make your notes? Interesting, isn't it? Now then, take a look at the entropy information. Because from a thermodynamic standpoint, the higher is its entropy, the more stable it is. Which of these forms of carbon has the higher entropy? Graphite, doesn't it? So guess what? From an entropy standpoint, as well as from an enthalpy standpoint, graphite is thermodynamically more stable than diamond, and that's why graphite is the most stable allotrope of element carbon. How about that? Which means if we're going to write sub-F reactions, we talked about the meaning of sub-F last time. Form 1 mole of the stuff in the phase desired from the required mole quantities of the most stable allotropic forms of the component elements. There's one exception to this, phosphorus. I'm pretty sure the exception comes as a consequence that phosphorus, white, is very reactive. That already tells you it's not very stable, as opposed to red phosphorus. But red phosphorus is so damned unreactive that if you try to make material with red phosphorus, I don't think you're going to get anywhere. So they use white phosphorus, reactive phosphorus, as the thermodynamic reference point, phosphorus. And we're not going to do anything with phosphorus chemistry, at least not now, so don't worry about that. All right? So the question is, how can this be? That the carbon diamond is far more durable and tenacious than the carbon graphite, if the carbon-carbon covalent bonds in graphite are stronger. Well, if you attack this problem with Lewis picture analysis, you'll see that here is an extracted Lewis picture for the carbon atoms in carbon graphite. Here's an extracted Lewis picture for the carbon atoms in carbon diamond. Carbon atom graphite is how hybridized? sp2. Carbon atom diamond, sp3. Well, you already know sp2 is associated with stronger bonds, don't you? Bond order, carbon-carbon bond order in graphite. What's the bond order for the carbon-carbon bonds? 4/3, isn't it? 1, 2, 3, 4 covalent bonds, 1, 2, 3 bond sites. But here the bond order is 1. So that tells you why the carbon-carbon bonds are stronger in graphite than they are in diamond models. The diamond model is a little bit small, so if you wish to come up after class and take a closer look at it, fine. Or you can Google this and you'll see all kinds of nice pictures. If you got your chemistry book, here's a case where you can use the book for something. It ought to have the diamond lattice picture in it and the graphite lattice picture in it. If I pick a reference point carbon, they're alternating colors just to make the component atoms of the model more easily seen. This kind of white looking carbon atom. Notice that this carbon atom has got 1, 2, 3, 4 nearest neighbor carbon atoms. Corresponds to the sp3 hybridization and the generally tetrahedral geometry associated with each carbon atom in the diamond lattice. But if I look at the graphite lattice and hold the model this way, I can see how this arrangement of carbon atoms from the graphite lattice relates to the picture I have on the board. Carbon atom, 1, 2, 3 nearest neighbor carbon atoms. Corresponds to that picture. I don't know how you can make a double bond with wires. So you're just going to have to imagine that this is a resonance stabilized arrangement of carbon atoms. But notice that all these carbon atoms, which are in this rather triangular pattern corresponding to sp2 hybridization for each individual carbon atom and 3 nearest neighbor carbon atoms, all these carbon atoms share the property of being in the same plane. Just like all these carbon atoms and just like all these carbon atoms. But if I hold the model this way for graphite, you see this large separation between this plane of carbon atoms and this plane of carbon atoms? Large separation. The reason why the model has been made like this, with this large separation between this plane of carbon atoms and this plane of carbon atoms, is that these carbon atoms, all the carbon atoms in this plane, are covalently bound only to other carbon atoms in the same plane. What do these long pieces of wire simulate? Van der Waals bonds, or London forces. Van der Waals attractions. Do you know how the magnitude or strength of a London attraction between a given pair of atoms compares to covalent bond strength? You learn something about that in 2045? If my memory is right, the covalent bond strength is about 1,000 times stronger than the London strength. A hell of a lot stronger, let's put it that way. However, as the model shows us, in the diamond lattice, every carbon atom is part of a covalent bond network. The only types of interactions between and among the carbon atoms in the diamond lattice are formal single covalent bonds. That's all you have. Here, you got an arrangement of covalent bonds for the in-plane carbon atoms with each other and London attractions. So when you shove your carbon graphite pencil across your paper and leave a smear of carbon atoms, you're doing this because you're breaking what? These covalent bonds? Nah. You're wiping out these London forces and leaving a smear of carbon atoms. You're sharing planes of carbon atoms from each other when you write with the graphite pencil. That also accounts for why this thing has the higher entropy. Because the wiggling factor between this plane of atoms and this plane of atoms is great. There's not strong bonding here at all. Whereas, again, for the diamond lattice, each carbon atom is part and parcel of a three-dimensional covalent bond network. So the wiggling factor is much less. Entropy much lower. And that's what the data shows us. One other important property of graphite, which follows from this Lewis picture.
What are the connections on the outside, the exterior carbon system?
Here,
Yeah,
just more carbon atoms.
right, but when you get to the end of the molecule, what do they bond to?
The end of the molecule.
Like you have model, right, that's a chunk of it. What's on the exterior carbon?
Nothing.
So they have negative bonds plus.
You can do the analysis to find out for yourself. But clearly the exterior carbon atoms can't any longer be part of this covalent bond network. But Avogadro's number of bonds times 4 in a mole of carbon atoms more than compensates for this lack of bond stability experienced by the exterior carbon atoms. I don't know what else to say beyond that at this stage of the game. What important property do you think arises as a consequence of the carbon atoms in the graphite lattice being part of a resonance network? Because there is no double bond in this thing, just like there are no single bonds. These are all resonance stabilized covalent bonds. Electrical conductivity. Because with this pi system that extends throughout a plane of carbon atoms in the graphite lattice, you have in fact a mobile pi electron cloud. That's this pi bond, which is equally a part of this bond site and this bond site all at the same time. And that extends throughout the lattice. In sum, for graphite, resonance accounts for the fact that this stuff is a pretty good conductor in the solid state. We'll talk more about that in chapter 22 on electrochemistry. Because carbon graphite electrodes are commonly used in electrochemistry. Because they're conductors, they're solid state, so obviously they can be used as electrodes, and they're not very reactive. So they serve the purpose of functioning as a cheap, effective, inert electrode. More on that in chapter 22. All right, now one more question on this business, just to try to make sure you remember what the superscript 0 means, as well as the sub F. Conditions, standard state. Pure liquids, pure solids, at an external pressure 1 atmosphere are in the solid state by definition. Solute species in a standard state at a molarity of 1. Some people use 1 molal. We'll stick with 1 molar. And gases, partial pressure 1 atmosphere for the gas for it to be in the standard state. Sub F. When you see this, it means you're considering a reaction involving the formation of how much stuff? 1 mole in the desired phase from the required mole quantities of the most stable allotropic versions of its component elements. So, with that being said, for Officers Candidate School molecule, OCS, Officers Candidate School, okay. We make Officers Candidate School by taking CO2 and replacing one of the peripheral oxygen atoms with sulfur. On your paper right now, I want you to write the equation for the reaction, which if observed at 25 centigrade, where OCS is a gas phase stuff, if we were measuring delta G for this thing under standard state conditions, we'd get delta G sub F super zero for OCS. What are the reactants? Can we start with this? Because diatomic oxygen is the most stable allotropic version of oxygen as opposed to monatomic oxygen or ozone. Sulfur. Do you know the formula for the most stable allotrope of sulfur at normal lab conditions? S8. Pretty sure it's rhombic sulfur. That has to do with its crystal structure. One-eighth. And at last, carbon. What allotrope? Graphite. And there you have it. And no other reaction equation corresponds to this. And now we go to section 21.2, where we will begin to lay foundation in conjunction with section 21.3 to do what I believe is the most important part of chapter 21. And that is to see how fundamental thermodynamic properties of substances, table 1, not only relate to fundamental thermodynamic properties of reaction systems, like delta H0 or delta G0 or delta S0. And you talked about the delta H0 part in 2045, at least I expect that you did. How does all that stuff relate to the most stable thermodynamic condition in which a reaction system can exist? What's that called? Equilibrium. Wonderful. So we're going to talk about an experiment. An experiment which, to some degree, we talked about way back in chapter 17. Maybe you will remember. Chapter 17, you remember this? We asked you to write a Lewis picture for this, a Lewis picture for this, stuff like that. In any case, now from a thermodynamic analysis standpoint, we shall imagine doing this experiment. Here's the experiment. A piston cylinder apparatus under normal lab conditions contains 1 mole of N2O4 gas. A second piston cylinder apparatus standing next to this one containing 2 moles of NO2 gas. So in here initially 1 mole of N2O4 gas only. Here initially 2 moles of NO2 gas only. If we were able to do these experiments, what would be the gee whiz volume? We'll take NO2 and N2O4 to have behavior describable by PV equals nRT, so-called ideal behavior. I heard 22.4, but remember, for gases, there is a defined temperature reference point. That's 0 centigrade. The volume occupied by a mole of ideal gas is 22.4 liters if the gas is at an external pressure of 1 atmosphere and what temperature? What temperature? 273 Kelvin, 0 centigrade. But we're talking about this at 25 centigrade. So you're going to have to do some arithmetic operation based on Boyle's law to answer the question about the approximate volume occupied by the mole of N2O4 gas inside this piston cylinder gadget. Will the volume be larger or smaller than 22.4 liters? Larger or smaller? Larger. This temperature is above 0 centigrade. When you warm gases, as in warming any sample of material, you increase the average kinetic energy of the component particles of the sample. So they move faster. That results in an increase in volume if you have the sample contained in a device whose volume is not fixed, like a piston cylinder apparatus. So 22.4 liters is the volume at 0 centigrade, 273 K. Tell me, Boyle, by what factor will you multiply this number by to get this volume? The temperatures in question are this at 273 K and our experiment, which we're doing at 298 K, right? So you can multiply this by 298 K over 273 K or 273 K over 298 K. Which is correct? We know the volume is going to be larger than this, isn't it? So, here's what we do. And if you did this kind of stuff in Chemistry 2045 with P1V1 equals P2V2, pooey on that. That's nonsense. It involves no thinking. And once you turn off the thinking, you quit learning. And none of that junk going on in my 2045 class. P1V1. Get the hell out of here with that stuff. M1V1. Get out of here. That's junk. Turns off the mind. So if you do this arithmetic, you'll find out that this volume is about 25 liters. Woo, we got to have a big piston cylinder gadget to do this by experiment, don't we? So this is going to be about 50 liters. How about that? A little bit less than 50 liters. Now then, back to the experiment. 1 mole N2O4 gas initially in here, colorless gas. 2 moles NO2 gas, brown. Remember this from our conversation about these gases in chapter 17? Thermodynamic information coming from table 1. In this direction, this reaction proceeds with an unfavorable change in entropy. But in this direction, which I asked you about back in chapter 17, this reaction proceeds with a favorable change in enthalpy because this reaction is strictly bond forming. This reaction has got to be exothermic. Because the only thing that's happening in this reaction is NO2 molecules are bonding to each other to make N2O4 molecules. It's strictly bond forming. Okay? And if I look at the thermodynamic data in table 1, I'll see that the value for delta G0 for this reaction at 298 K is 4.7 kilojoules. Now, is it plus 4.7 kilojoules or minus 4.7 kilojoules? Well, the answer to that depends on this. Which one of these is bigger? So I'll tell you, this is bigger. So this reaction as written, is it spontaneous, yes or no?
No.
Remember, these are absolute magnitudes. Forget signs. Spontaneous, yes or no? Yes. Spont. So in this direction, minus 4.7 kilojoules. So this tells us that at 25 centigrade, which sample of material is more stable thermodynamically? 1 mole of N2O4 gas or 2 moles of NO2 gas? Which sample of material is more stable? I'm listening. 2 moles of NO2 convert spontaneously to 1 mole of N2O4 at 25 centigrade, 1 atmosphere pressure. Didn't we just show that? Well then, which sample of material is more stable at 25 centigrade? 2 mole NO2 gas or 1 mole N2O4? 1 mole N2O4. So back to our experiment. In the first cylinder, I'm starting with a mole of N2O4 gas at these conditions. 2 moles of NO2 gas in the second. So as to eliminate any kinetic barrier to the outcome of this experiment, we'll imagine we let this stand for a very, very long time, infinity. How about that? Long enough? And we'll open up each piston cylinder gadget. We want to analyze composition. What shall we see in this first cylinder? Will we see N2O4 only? What shall we see when we open up the second cylinder? Will we see N2O4 only? Will we open this up and find NO2 only? Will we open this up and find NO2 only? What will we see? We'll see this. Here is this mixture of NO2 and N2O4 at 25 centigrade. Well, it's about 23 centigrade in here. Do you think this is NO2 only? Because NO2 is the brown stuff. You think this is NO2 plus N2O4? Because the most stable thermodynamic system is shown when the system is at what conditions? Equilibrium! So what we're going to see if we did this experiment is that the volume of this would increase because some of this would fall apart and become NO2, while this volume would decrease because these would get together and become N2O4. So you wouldn't wind up with pure NO2 or N2O4 in either, because neither is as stable as the equilibrium system, which is represented by this graph. So in preparation for our conversation on Friday, I want you to look at this graph, and I want you to read section 21.3. That's where we're going to be at Friday.